Hey, welcome to the Narwhale Network and this video on dynamic constraints and animated objects. Before we start, a quick overview of the scene file I'll be working in. All of this here is just to create some box geometry for us. I'm applying some point color, blue for boxes that will be dynamic and red for ones that will be animated. We create a name attribute. This attribute wrangle here is just applying active and deforming attributes to the appropriate boxes. This transform node is just setting up a rotation animation using $F times 10. And of course, we're only rotating box 0, as you can see. There you go. That feeds into our DOP network, where all the magic will happen. So today we'll be attaching, or pinning, dynamic constraints to animated geometry. Just like the ball and chain that was seen a few moments ago, the chain, of course, was set up with cone twists, and the first of those cone twist constraints was pinned to the animated geometry of our character model. So let's get started with something just a little bit simpler. I'll be breaking things down using 3 boxes, the first of which will be spinning, and the other 2 will try to constrain to this spinning box and have them follow it around using soft constraints. Alright, so getting straight to setting up our constraints, let's start from here, which is the last place our geometry was unanimated and unpacked. So great rest geometry to build constraints from. I'll be using connect adjacent pieces to build my constraint geometry. Perfect. Seems like we'll be needing a higher search radius. I'll go with 0.5 for now for my scene. And I'll go ahead and create a length rest attribute, rest length. There we go. We'll need that later since these points are a certain distance apart. And then I will set up an attribute wrangle, and we can use it running over primitives to create my constraint attributes. So at constraint name. And I'll set this up to be named capital soft for our soft constraint. Cool. We can go ahead and pipe this into the second input of our DAP network and go set it up inside. I'll need a constraint network. We can put it into this conveniently placed gap. It's almost as if I have this pre-prepared. And since I'm using bullet, I'll be setting up a bullet soft constraint relationship node. There we go. And of course our data name matches our constraint name attribute up top. And everything seems to be set up correctly, except we need to make sure our constraint network is accepting geometry source from our second context geometry. Great. So this is set up, our constraints are generated, and if we press play, yeah, that's the result we get. It's clearly not exactly what we want. Let's go into how we really set this up to work with animated geometry. So the solution, and the important part of this video, is to deform the constraint points ourselves to match the deformations of their parent geometry. So we only need to deform the points directly attached to the animated geo, because they're the only ones that seem frozen in place in our DOP net, right? Cool. So let's go out back to object level, and we can try and set this up. Robert from editing here. All of this should work inside of a DOP net in a SOP solver, but for simplicity, I'm working in object level. I'll be deforming our constraint geometry here, which will force this geometry to update inside of our DOP net. As mentioned before, though, we only want to be deforming points directly associated with our animated geometry, and taking a look at those constraints, that means these 4 points down here. Alright, so I'll set up a point deform node to handle this. There we go. We can pipe in our constraint geometry. My rest point lattice will come from up here, and the deform point lattice from our animate box. Great. So that makes our points deform, but too many points are deforming. So I'm going to go ahead and set my maximum radius down to 1 so we get the nearest point. For group, I'm actually going to filter out all the points that are associated with non-animated boxes. Coming in from our connect adjacent pieces, if we look at our geometry spreadsheet, we'll see that all of the constraint points associated with box 0 have inherited box 0's deforming attribute, a deforming value of 1. So at deforming equals 1 inside of our point deform, and that should take care of things. Only those 4 points are now capable of deforming. Great. So piping this into our second input of our DOP network, we should see results right away. Now our boxes are deforming the way we would expect them to. So really this is great. We've set up our constraints between animated geometry and active geometry, and they're following each other around the way we want them to. But there still seems to be something wrong with it. This box is tilted around a bit strangely. Let's go and investigate inside of our DOP net and take a look at what's happening. So as you can see, the constraints seem to be drifting, keeling over. There's some sort of angular drift that's happening, and that's not what we want. We'd like them to stay, remember their original positions, and kind of stay nice and rigid. Unfortunately, I've found that messing with angular stiffness in our constraint relationship node doesn't really help much. It does not fix this angular drifting problem. There is, however, a workaround, and that was just to shrink our constraint geometry down to a length of 0. With both points on top of each other and sharing the same location, there will be no possibility of angular drift, right? So we can set that up in object space right after I connect adjacent pieces, drop in a primitive node, set our do transformations on, scale things down. We can see our constraint shrinking, right? We no longer need a rest length attribute here, at least in my example, so I'll be disabling that. And inside of our .NET, make sure the bullet soft constraint node has its rest length value set to 0 as well. Going back and playing through it, we can now see that those constraints are not drifting the way they were before. This system should of course work with any kind of dynamic constraint. You'll remember the example in the beginning of the video with the ball and chain. I'll throw that up on screen again right now. But in this example, of course, we're using cone twist constraints, just the same way I've set up these soft constraints. So it's quite adaptable, and I hope you guys found this interesting. Hey, so you watched to the end of the video. The next one's going to be on custom control fields in the Pyro solver, so stay tuned for that. You might even want to get subscribed.